Data Skeptic is the official podcast of dataskeptic.com, bringing you stories, interviews, and mini episodes on topics in data science, machine learning, statistics, and artificial intelligence.
So today, Linda, I wanted to talk about convolutional neural networks.
Neural networks. We talked about it on the show previously.
Yeah, we've been on a little kick of deep learning topics.
Why don't you remind us what it is?
Oh, good idea. So a neural network is a data structure, a model of sorts, inspired by the brain, loosely inspired maybe. You have a set of neurons. So let's just describe one neuron. It's a computational unit, at least for our discussion. It has a bunch of inputs, as many as you'd like, and then you do something with them. That might be add them all up. Then you usually apply some function to them, like an activation function, they call it. Typically, that's something like a logistic function so that you get between 0 and 1, just so you don't have runaway values, and that's the output of that neuron. Now, here's the kicker. That output can then be the input for one or many more neurons in another layer. So if you stack these things up layer by layer and use some of those techniques we've talked about previously, like backpropagation, you can often optimize the weights of that network, which is how much neurons rely on other neurons and which neurons they rely on, to do something useful, like facial recognition or, estimating the number of calories in the food in a picture. Even machine translation is a good one too.
So stacking them is the neural network.
That's right. That's what kind of makes it deep. I mean, there's always been layered neural networks, but somewhere along the way, people were like, man, we got a lot of layers. Let's call it something different. And that's deep learning.
Oh, okay. So it's just a trend. Okay.
Yeah, in a way, but a very important trend.
So let's go back. What was the word that you mentioned?
Convolutional neural networks, or CNNs.
So tell us, what is that?
Everything about deep learning and neural networks, or one of the main things, falls under what I call architecture. How do you build them? How many layers should there be? How connected should the layers be? There's all these choices in how you structure it. CNNs in particular that we're about to talk about tend to work really well for photographs and images and stuff. I'm sure it applies well in other areas too, but that's where you see most of the really cool examples. So what makes a CNN unique? Let's do that. First, before we define it, let's just talk about image recognition a little bit more. Now, if we made what's called a fully connected network, that would mean that every pixel in your image maps to a neuron, actually maps to all the neurons, and each neuron independently can decide how much weight it wants to put on each pixel. Now, in theory, it would be possible for a fully connected neural network to be able to learn how to recognize what type of animals in a picture. But it would take a huge amount of training data and a huge amount of compute time because it's really inefficient. There's no communication then between the neurons. Does that make sense?
I don't know. I kind of zoned out.
Well, let's get more technical then and bring it back around. Let's talk about a property called translational invariance. Let me put it to you this way. If I showed you a photograph of a cat, you would recognize that it's a cat, right?
Hopefully.
And what if I moved it 1 inch to the left? Would you still be able to recognize that it's a cat?
Well, I don't know the ratio of this photo, but assuming your photo is 9 by 9 inches, I could probably still recognize.
Right. So you as a human being have this kind of amazing task that your vision works everywhere, right? If I put the photo on the ceiling, you might ask me, why is there a photo on the ceiling? But you could still recognize that it's a photo of a cat.
Yeah, I mean, at the dentist, we have photos on the ceiling.
What kind of dentist do you go to?
It's a kid-friendly one.
Why do you go to
He posts pretty photos of the desert and rainforests. He's a nice guy. I like him. He's a dental hygienist, to be clear.
And if he spins you around loop-de-loop in the chair, from all the different angles, you can still see that photo of the dentist, right? Of the desert, right?
I mean, it takes longer to figure it out, right? But yeah.
Maybe a little bit, yeah. So that is a property called translational invariance. So that no matter what the shape, scale, different pitch, or whatever you call it, you move the image around, you can always recognize it the same. Now, that wouldn't be true if we had this fully connected neuron where it mapped to specific pixels. What we'd really like is a neural network that even when you move the image around a little bit, scale it up or down a little bit, it could still fulfill its task.
So to fulfill its task means someone recognizes it?
Let's talk about facial recognition. What if you had this piece of software that did really good facial recognition, but it only worked when the face was in the exact middle of the photograph?
I mean, that's only useful for photo IDs then.
Yeah, exactly. So in fact, I think that's why we saw a lot of technology like that ahead of its time when they could constrain the problem really well. But in general, like you log into Facebook, you could just have a photo at any place in the image and it wants to recognize it. So that's this property called translational invariance. And the way that's achieved in CNNs is that even though you have this big neural network that's connecting all the input pixels to the various neurons, the weights on those neurons repeat themselves. So what you do is picture like a photograph and then cut out a little tiny group of pixels in the upper left-hand corner, let's say like 10 by 10. And that is alternatively called a filter or a kernel or a pixel group or sometimes a window, but just a small segment, right? Take that 10 by 10 window, shift that over 10 pixels. And well, actually, that's another parameter. How far do you shift it over? That's what's called the stride. I think a lot of people use a stride of 1, just shift it over 1 pixel. You could shift it over 10 and then it'll like perfectly tile, right? But that's a decision you have to make when you architect this thing. So shift that window and then shift it again all the way to the right and then start a new row just below it. So you have this window that's almost like scanning the whole image. You create all these different groups of neurons that use the same exact weights but are positionally different in the space of the input. So ideally, if you train this network to recognize pictures of birds, let's say, and all the birds are near the top of the images, if then later you try and generalize the network and run it on a picture where the bird's at the bottom, it should still recognize the bird, even though it's never seen one with a bird in that position before, because it knows how to recognize birds from the training. And the training is translationally invariant. You're using the same weights all over the whole place.
Same weights all over the place. What does that mean?
That little, let's just call it the filter, that 10 by 10 grid of neurons. Those are connected to 100 different pixels in the image, right? So they only see a small piece of it, a 10 by 10 pixel square. And that's not the whole image. So they can't possibly say, oh, there's a bird in this picture, because they might be looking at a part where the bird doesn't exist. They can learn to recognize other features like edges or maybe a leaf or a bug, just very simple kind of shapes and stuff. And that would be like your first layer in the neural network. Then you might have other convolutional layers that are looking not at the pixels of the image, but the output of those little filters, those 10 by 10 things. So maybe the next layer is smaller. Instead of having all these 10 by 10 shapes, it has some 7 by 7 shapes. Its inputs are the outputs of the first layer. It can start to recognize more complicated things from these groups of lower level elements.
So what does weighted the same mean? How do you not weight it the same?
Well, that would mean if like you had all of these, you cut up your image into, let's just say you cut it up into 10 rows and 10 columns and you had 100 squares that each had, some number of pixels in them. You could treat all of those independently and say like, all right, I'm going to give these to 100 different image recognition teams. You all go learn this part of the image and don't talk to each other. No collaboration. That would be very inefficient and probably not work.
But isn't that equal weight?
No, in that situation, every one of those subsections could end up with different weights.
What are weights, though?
Weights are the emphasis you put on each of the inputs. So if the weight is low, you say, oh, that pixel doesn't tell me anything. If the weight is high, you say, wow, that pixel's really important. I want to be sure that I light up if it's lit up.
Okay, so equal weights means even if there's just white space in the pixel, they view it as the same importance as something else.
That's exactly right. So since the weights are shared, all of those subsections are one learning task instead of n squared number of learning tasks. Here's an interesting analogy why I picked a bird. If you look at a bird, what is it mostly composed of?
Feathers.
There you go. Do the feathers on the top of the back look very different from the feathers on the bottom of the back?
Depends on the bird.
Yeah, it depends. And obviously they have longer tail feathers and shorter face feathers and stuff like that. But by and large, the texture of feathering has some consistency to it, right?
Yeah.
If I came in with a suit that was out of a fabric made of feathers, that was the design, you'd be able to say it repeated in places, right? Most likely.
Yeah.
You don't have to look at the whole suit to recognize that it's made out of that texture. You can look at one squatch and... No, squatch is a Bigfoot. One swatch.
I was like, you're going to need to define squatch for me.
Hey, we're a couple of years in. I can just make up words at this point.
Kyle's making up words for you guys.
The host is allowed
guys
that
and
privilege. Yeah. So if you were able, let's say, learn a texture, like the feathers of a certain bird or the fur of a cat, that learning exists in one section of the neural network, one filter, but it applies everywhere. So if there's a way that your network gets good at detecting fur or feathers, then at the second layer, you'll have all of these neuron groups saying, hey, I've got fur in my section. And then maybe its neighbors will also say, yeah, we've got fur too. And you might infer that this little bundle of fur balls is a dog or a cat or something.
Well, you could say it's a mammal.
All mammals don't have fur.
We're not biologists, so we won't talk about
that's abundantly
specifics.
True, yeah. But yeah, that's what makes, then there's a lot more to be said about CNNs, but the gist of it, which we're going to try and do in this mini episode, is it's a type of neural network architecture. I've specifically talked about it in terms of like one layer, that it's these filters or kernels, groups of pixels, that you repeat, you shift over the whole image. So it's like you were one person trying to learn something, and to do that, you look at these very small segments across the whole picture.
The grid.
The grid. So a grid is a nice analogy. It's good to think of it as a grid, but actually because the hyperparameters have the stride, how it shifts, they do overlap. It's not like they're completely separated by a grid, although you could make them do that and it might work okay. Usually you just shift it one pixel over and you repeat. And if you repeat that over the whole image, it's able to develop the ability to recognize and find features in that image that work everywhere. They have translational invariance. There are reasons you might want to deviate from that. For example, in recognizing things about a person, obviously your eyeball is a little bit different than where your mouth is. It would be better if, you could have the convolutions kind of mapped out, with local features. So there's a lot of like work and how you do stuff like that. But just the plain vanilla convolutional neural network, it's the same learner spread out everywhere in that grid, so to speak. And then you almost assuredly need more layers of convolution where you're built on top of the previous layer. And there's more to be said about the architecting these things. Like you're going to have pooling layers and all types of stuff like that to make a CNN work in most cases. But those are good topics for another day. The core thing about CNN is that it simplifies the curse of dimensionality by having just one set of weights you're trying to learn that shift across the whole image.
Yes, very robotic. Well, I'll have to remember this for the future topics when we circle back.
That's right.
When we build out the future. Is there any hope in you talking about it soon so I don't forget?
Well, we can record every day if you want.
Well, I think that would help me sound more educated.
All right. Maybe we can
informed.
Let's do pooling then in the next couple of days.
Okay, pooling.
Yeah.
I look forward to going to the pool.
And my favorite mnemonic, if you're interested in thinking about this property, translational invariance, that's really the key to CNNs. And think about pictures on the ceiling. If you can recognize them there as well as on the floor, that's a nice property human beings take for granted that we can do.
Translational what?
Invariance. Not
so
easy.
That's a skill?
Yeah, it's a skill.
That's good. I wonder if dogs, cats, and birds know that.
Well, certainly they have that ability. I'm not sure if they're conscious of the fact that they can do it.
Yeah, I mean, if their toy was upside down, they know it's their toy still.
Right, good example.
Or if I were upside down, my cat, if I had a cat, would still know it was me.
Somebody told me if you move a beehive more than 3 feet, the bees can't find it again.
Oh, goodness. Kyle thinks he's a biologist.
I tried to look this up on Snopes. They had a bunch of fun stuff about bees, but they didn't answer this question.
I don't know.
I think that's a dubious claim. But what I did learn is that bees do interesting things to remember where they are. They probably would have a little bit harder time finding it, but I can't imagine. And if you move it 3 miles, then yeah, they're not going to find it. But 3 feet sounds a little bit too small.
I feel like they could find it 3 feet away.
Oh, absolutely.
But, this is not for us to discuss because you are not a bee scientist.
Not yet.
So let's just rein it in and let's edit it out.
Well, we had some great blog posts from a guest blog poster on bees on Data Skeptic, so people should go check that out in the archives. That was fun.
Well, maybe in the future there'll be honey that's branded Data Skeptic honey.
Check the store. We have T-shirts and pins and stickers. Maybe there'll be honey soon. I have a feeling the mugs are going to be there sooner than the honey, but you never know.
Oh, yeah. Well, you could put honey in the mugs with your tea.
Oh, we could have a little gift box then. All right, yeah, check out the Data Skeptic store for all those things.
Keep an eye out. We'll push for it.
Fantastic. Well, thanks as always for joining me, Lindy.
Thank you, Kyle.
And until next time, I just want to remind everyone to keep thinking skeptically of and with data.
Data Skeptic is a listener-supported program. To support the show, visit dataskeptic.com and click on the membership tab.